Okay then, so in this video what I want to do is to go over some results about exponential objects and then say what they mean for power objects. So um, one of the basic kind of things that we want to be able to do, I mean, when you first learn about exponential objects, you learn about how the exponential object is defined and this idea that you can find this unique transpose, etc. But when you get into wanting to do more manipulations, you really want to be able to um, use this evaluation arrow in a very kind of free way. So there's this result which basically tells us if we have an arrow from h into b to the power of a times a, and we want to compose it with the evaluation arrow, then this result tells us what we get. So in particular, let's call the arrow from h to b to the power of a s transpose, and we'll call the other arrow from h to a x. So this result says that E after s transpose comma x is equal to s after the identity of h comma x. And this result for us is going to be a kind of bedrock that we're going to look at special cases of, and we'll basically be using this theorem and specializations of it to talk about lots of interesting things. So what's the proof to it? Well, basically, it's just that this diagram composes. So this triangle on the right, it's just that this diagram commutes. So this triangle on the right commutes because of the definition of S transpose. And this triangle on the left commutes. Well, you can prove that. It's not very difficult to prove. Just compose this with this, expand it out, and you see that you get S transpose comma X. And so then what we have is the E after, well, okay, so let's go this way. What we have is the S after identity H comma X, that's going this way around, is the same thing we get as going this way around, is the same thing we get as going this way around. So that's the proof. There's an interpretation of this in terms of, you know, when H, A, and B are all real numbers. So this is basically the graph of X. So we can think of it like this as a sort of graph in the plane. And then doing S on a point of this graph gives the point in this surface, which denoting with these purple surface lines here. That's the point of S, which is above this point. So what I'm saying is if we pick a H, then doing identity H of X on that little H, and then doing S on it is basically getting the point H across and XH up. Well, H across and XH away from us, I suppose. And then S would be the point on the surface above that. And we're saying that that's the same thing as we get if we do evaluation after S transpose X on XH. So the idea here is we get this point X of little h, And then when we do whoops, I want to be an H there. Excuse me, I've got a bit wrong with this. So for this second bit, what I should say, what we want to show that this is equal to is E after S transpose H, comma XH. So what we're doing here essentially, we get our point H here. We find S transpose H, that's this function. Whoops. That's this function going away from us. And then we evaluate that at this point XH along, away from us. And that'll give us the same thing. So it's just two different ways to talk about the same point in the surface. One is like drawing a graph and then finding the point on the graph and finding where the surface is above that graph. The other one is sort of drawing this curve away from us and then evaluating it on this point, okay? So that's a little interpretation, but anyway, it's the result that's the important thing. Right, so specializations of it then. This thing I'm calling result 3 is a special case of theorem 1 where S transpose is equal to the name of R after exclamation mark H. So here at the bottom we have our original result. Again, we suppose that we have this X as an arrow from H to A, but now our S is name of R after exclamation mark H. So here's our original result, and then here's our new result. And the point here really is that because the name of R after exclamation mark H, we can show it's actually equal to R after P2 all transposed. Then, which, you know, in our case is equal to S transpose. In our case, when we put the S here, I mean, here we'd have S after identity of H comma X. Since that S is going to be R after P2, it just knocks out this identity, so we just get R after X. So this is a very useful result. The main thing to remember is this stuff here, okay? That basically when we're doing the name of an arrow, well, something that sends everything to the name of an arrow in b to the power of a, and when we pair that with an x and do the evaluation arrow, the result is just r after x, okay? So in order to prove this, we need to prove this result here. And we can do this. So I mean, basically what we want to do is we want to find the S such that S transpose is equal to the name of R after exclamation mark H. Well, the name of R is just R after P2 all transposed. And so we just get these black arrows to the right and we times all this diagram by A. And so we get these arrows like so. And we put an evaluation arrow on the end. And we notice that these two composed gives R after P2. And so we have R after P2 after exclamation mark H times 1A is equal to E after RP2 transpose times 1A after exclamation mark H times 1A. Well, that's just E after RP2 transpose after exclamation mark H, and RP2 transpose is name of R. So this is equal to then E after name of R exclamation mark H all times 1A. But also just using the idea of exponential objects directly, we can just write RP2 exclamation mark H times 1A is equal to E after the transpose of this times 1A. And then using the property that this transpose arrow should be unique, we have that this arrow here must equal this arrow here. And this arrow here is actually just S transpose for us. So we have that S transpose is R after P2 after exclamation mark H times 1A all transposed. And so we have that S equals R after P2 after exclamation mark H times 1A. And then we just sort of simplify that and we find it simplifies to R after P2. So to summarize then, the result we already have is that E after S transpose comma X is S after identity of H comma X. But we've shown now in our case where S transpose is name of R after exclamation mark H, we have that S is just equal to R after P2. And so in this case, we have that E after name of R exclamation mark H comma X is just R after P2 of identity H comma X, which is just R after X. So there we have it. I'm calling that, I think I'm calling it, yes, result 3. So, okay, here's result 3 again. We don't really need that step. That's just a that's just an intermediary step. Okay, so here's the main result then. Result 3 stated again. For an arrow name of R, exclamation mark h from capital H to b to the power of a, and an arrow x from h to a. We have the e after the name of r, exclamation mark h, comma x, is just r after x. Now, a special case of this is the case where capital H is the terminal object, and in that case we simply get the e after the name of r, comma x, equals r after x. And here r is just an arrow from a to b. So those are the general results, and then let's apply them to thinking about when stuff's in power objects. Okay, so we start to apply these results to power objects. So this first result, theorem 1, let's look at a special case of this where b is equal to the subobject classifier omega. So we have this notation. Let's get a colour so I can point out things better. We have this notation, x is in a S transpose. That's really just shorthand for saying e after S transpose comma x sends everything to true. And since we've shown that e after S transpose comma x is S after identity of h comma x, we have that this holds true if and only if S after identity of h comma x is equal to t after exclamation mark h. So this is equivalent to saying this statement in blue, and this clearly holds if and only if identity of h comma x is in the subobject classified by S. So this basically gives us a kind of general formula for when an arrow x from h to a is going to be in a subobject, but in terms of evaluation arrows and power objects. Now, the other results basically give special cases of this. So what this one does for us, when we have a name of r, well, okay, so we look at this result 3 here in the special case where b equals omega. So basically, in this case, the name of r is of course going to be a point of omega to the power of a, and then it's going to correspond to an arrow r from a to omega, or we can think of it probably more visually as a subobject r star. It corresponds with a subobject r star of a, okay, the subobject classified by r. Anyway, in this case, our result says that x is in a name of r after exclamation mark h. Well, that's just shorthand for saying e after name of r exclamation mark h comma x sends everything to true. And we know that e after name of r exclamation mark h comma x is equal to r after x. So this orange statement here holds true if and only if r after x sends everything to true. And that happens if and only if x is in r star. So we have this kind of simple way of saying when a general arrow x from h to a is going to be in this subobject of a corresponding to the name of r. And then finally, the simplest result, it's just like pretty much a special case of the last one. So we have this result 4 here, which is just the special case of the above, when h is a terminal object and here x is just going to be a point of A, and we're going to have the x's in a name of R if and only if x is in R star. Okay, so simple stuff. Right then, so time for something a bit different. These arrows between exponential objects have some interesting kinds of interpretations when we're thinking about power objects. So let's just recall, this is a result I discussed in my video on exponential objects. If we have an arrow f from B to C, then we can kind of exponentiate it. So we can define this arrow f to the power of A as f after E all transposed. And this is such that if we have any arrow h from A to B, we have that f to the power of A after the name of h is the name of f after h. Now, an application of this is when C here is the subobject classifier omega, because in this case, f here is going to be an arrow from B to omega, so that's going to correspond to a subobject f star of B. And we have this result that f to the power of A on the name of h equals the name of f after h. So how can we interpret this arrow f after h? Well, in this case, we've got that f is this arrow from B to omega, so we're going to have this subobject f star, the subobject classified by f, or if you like, the pullback of true along f. And then we're interested in the interpretation of this arrow f after h, and we can basically think of this as the pullback of f star along h. So in summary, in this case, we can think of this arrow f to the power of A. It sort of takes in the name of some arrow from A to B, and then it sort of sends that arrow, in a sense, to something corresponding to the subobject of A that we get by pulling back f star along h. So it's a very interesting kind of operation. Okay, so that's one kind of arrow between exponential objects. The other main kind is like this. So if we have an arrow G from an object A to an object A dash, then we can define B to the power of G. It's an arrow from B to the power of A dash to B to the power of A, and it's defined as E after identity times G all transposed. Now this has the property that for an arrow K from A dash to B, we have that doing B to the power of G on the name of K gives us the name of K after G. And this also has some very interesting applications. In fact, it's probably more well used than the other one. Basically, because this is this sort of internalization of this idea of this kind of pullback functor between these kind of sub A kind of partially ordered sets of sub-objects that I was talking about before. I mean, that the way I was talking about that in the essentials of topos theory videos, basically that that's, you kind of externally build this category that has these objects as sub-objects of A, and these kind of arrows representing inclusion. But really, that structure is properly represented by the power object, omega to the power of A. And then between such sub-A kind of partially ordered sets, there are these like monotonic functions where we just pull everything back along a particular arrow. And these kind of B to the power of G arrows are the kind of internalization of those kind of ideas. So let's see this. So the application then of this result is when b is equal to omega, obviously. So in this case, if we have this arrow g here, just an arrow from a to a dash, then we have this omega to the power of g arrow going from omega to the power of a dash to omega to the power of a. And if we compose that after the name of k, we get the name of k after g. Okay, so how can we interpret this? Well, I mean, k basically corresponds with an arrow from a dash to omega, and then there's this sub-object k star of a dash, which is the pullback of true along k. And then this arrow, the name of k dash, corresponds basically to the pullback of k star along g. Okay, so the way we can think of this omega to the power of g arrow is it takes in this point of omega to the power of a dash, this kind of point of omega to the power of a dash corresponding to a sub-object of a dash, and it sends it to the pullback of that sub-object along g. Okay, in other words, g to the minus 1 of k star. Now, there's another kind of interesting application of this if we consider the special case where a dash is the terminal object. So in that case, we must have that this arrow g equals exclamation mark a, and also we must have that k is just going to be a point of omega and so in this case our kind of exponentiated arrow is omega to the power of exclamation mark a, and that's going to send the name of k to the name of k after exclamation mark a. And so how are we to interpret this arrow k after exclamation mark a? Well, basically our k here is picking, it's a sort of point of omega. So this is an example in the category of graphs. So you pick one of these points of omega, and then what you get when you do this is you get a point of omega to the power of a, so it basically corresponds to a sub-object of a, and it's going to be the point, the name of k after exclamation mark a. So what is this point? Well, essentially you just have this arrow k after exclamation mark a, which sends everything in a to this particular point in omega. So if k is the true arrow, then this composition here, purple arrow after red arrow, would send everything to true, and then the sub-object it's classifying would just be the full sub-object of a. If k after exclamation mark a sent everything to false, then you'd be classifying the empty sub-object of a. In other words, k after exclamation mark a or starred would be the empty sub-object of a. But in this case, see, there's this point, point of omega in the case where we have the category of graphs that is neither true nor false. It's this point that, you know, if we send an edge to this loop M here, we're basically saying that that edge is absent, but its source and target are present. And in particular, this k after exclamation mark a, if that's sending everything to that, is sending all the edges to that loop and all the vertices to its source and target, well, the sub-object that composition k after exclamation mark a is classifying is basically just the graph that just has all the vertices of this graph A and none of the edges. So it's a kind of sub-object we get by stripping away all the edges of our graph. Incidentally, so let's give this a name. Let's just call this sub-object, well, the source of the sub-object D here. And let's give this arrow a name. Let's call it, I don't know, zeta, let's say. So incidentally, remember that hom v comma blank is just a single vertex. So I believe in this case, I might be wrong, but I think d to the power of hom v comma blank, this exponential object, I think in this case it's just going to have points, and there's going to be a point for every arrow from the single vertex into D. So I think, and I'll have to check this, but I think this just corresponds in this case to this graph, which has 3 isolated vertices. So basically, if you want to convert a graph to a load of points, one point representing each of its vertices, this is a way you can do it.